Let's talk about conservation laws in general, and then we'll move on into parity. What do we mean by conservation laws in quantum mechanics? There are two working definitions. One is, if Q is an observable that's conserved, the expectation value of Q will be independent of time. Another definition is the probability of getting any particular value of the expectation value of Q is also independent of time. What we want to figure out is, when does each definition hold? Let's stipulate that dq dt is 0, which tells me that my expectation value of Q is independent of time. Also, this commutes with the Hamiltonian. So the probability of getting result, let's say Q sub n, let's say my result when I take an expectation value is little q sub n. The probability of getting such a result, q sub n, is equal to some function f sub n times my wave function squared. And the assumption being q sub n operating on f sub n is equal to my little eigenvalue operating on my eigenfunction f sub n. Moreover, it also says that psi of t can be written as sum over m e to the minus I e sub m times t over h bar times c sub m psi sub m. Assumption being psi sub m are all eigenstates of the Hamiltonian. This means that the probability of obtaining eigenvalue q sub m, say q sub n, is equal to sum over m e to the minus I e sub m t over h bar c sub n f sub n psi sub m quantity squared, whole thing squared. Since Q, capital Q, and H commute, we can find a set of simultaneous eigenstates. So that being the case, we'll let f of n equal psi of n, since they're going to be the same. And also, since psi of n is orthonormal, it's fair to say P of Q sub n is equal to sum over m e to the minus I e sub m t over h bar c sub m psi n psi m squared. And of course, the only term that will survive will be when psi n equals psi m, since they're orthonormal. That gives me c sub n squared, which is the probability of this occurring, and it's obviously independent of time. So 1 and 2 both work. Let's apply this to the parity operator. We'll do one dimension first. So one dimension parity operator, I'm going to apply capital pi, that's my parity operator, to wave function psi of x. That gives me psi prime of x, which is, as we said before, psi of minus x. Pi is its own inverse, which means pi to the minus 1 is equal to pi operator is also equal to the Hermitian conjugate of pi. So it's Hermitian, and it's also unitary. So operators transform under spatial inversion in the following way. q prime, my operator, is equal to pi dagger times q, it's pi. And so, for example, momentum operators and position operators are of odd parity. So if I take my position operator x prime, I apply my parity operator, pi dagger to x, pi, that's going to give me minus x. And the same thing for momentum. P prime, if I apply my parity operator to P, I'm going to get minus P. So if Q is a function, if my Q operator includes things like X and P, then the following case, if I apply my parity operator to Q of X and P, I'm going to get Q of minus X and minus P, even if I put them together. System has inversion symmetry if the Hamiltonian is unchanged by a parity transformation, which means that if I apply my parity operator to the Hamiltonian, I just get the Hamiltonian back. Or if I want to use the unitarity of the parity operator, I can say H and the parity operator commute. So given a particle of mass m in a one-dimensional potential v of x, if I have inversion symmetry, that means v of x is equal to v of minus x. It's an even function of position. So what are the implications of inversion symmetry? Well, there are a couple of them. First is, I can find a complete set of simultaneous eigenstates of my parity operator and my Hamiltonian. And we'll write those eigenstates, and we'll write them as psi sub n. So pi applied to psi sub n of x is equal to psi sub n minus x, which is equal to plus or minus psi sub n of x. The eigenvalues of parity operator, remember, are 1 or minus 1. For a potential that is an even function of x, we can choose the stationary states that are even or odd functions of x. So, for example, I could apply this to the harmonic oscillator. I could apply this to the infinite square well, delta function, and so on. So that's one implication of inversion symmetry. The second is, by Ehrenfest's theorem, time derivative of my parity operator, I can write as I over h bar times the commutator of h and the parity operator. Of course, that's 0. H and parity operator commute, therefore the commutator is 0. Means that parity is conserved for a particle in a symmetric potential. And that's going to be true for all time. Okay, that's neat for one dimension. Suppose we go to 3 dimensions. We apply the parity operator. As we said earlier, what that's going to do, if I have a function of x, y, and z, that's going to change it to minus x, minus y, and minus z. If that's the case, let's apply my parity operator to some function psi of r, and that's going to give me psi prime of r, which is just going to be psi of minus r. R and P, similar to the one-dimensional case, they're going to transform in the following way. R prime will be equal to pi dagger r pi which is going to be minus r. P prime will be equal to pi dagger P pi minus P. Any other operator that's a function of r and P, call it Q. Q prime of r and P will then become, obviously, Q of minus r and minus P. What about vectors like r cross L? What about angular momentum? R cross P, rather. This is odd. Vectors like angular momentum are even under parity transformations because x is odd and p is odd. We call these guys pseudovectors. Real vectors will retain their parity. They're going to be odd under parity. Real vectors like, well, they're all real vectors, but pseudovectors are even under parity transformations. Regular vectors are odd under, like x and p are odd under parity transformations. Turns out that scalars that are odd under parity transformations are called pseudoscalars, whereas scalars that are even under parity transformation are just plain old scalars. In 3 dimensions, the Hamiltonian of a particle of mass m moving in a potential v of r has inversion symmetry if v of r equals v of minus r, just like the one-dimensional case. This is going to work for any central potential. So just like in the one-dimensional case, parity will be conserved. So in other words, if I apply my parity operator to psi sub n, l, m of theta and phi, if hydrogen atom or whatever the case may be, I can write that as minus 1 to the l psi sub n, l, m, r, theta, and phi. What about selection rules for parity? Selection rules tell you when a matrix element is 0 based on symmetry. If a matrix element is 0, then there's no transition that can occur, or I should say a transition is forbidden. So we can write a matrix element, let's see, we can write this over here. So I can do the following. I can write a matrix element as B, QA. An expectation value is actually a special case of a matrix element when in this is what we call a matrix element, just to clarify. Of course, an expectation value is when B and A are the same thing. Right? This is what we call an expectation value. That being the case, let's look at the electric dipole moment operator. We'll call that P sub E, electric dipole moment. I write it as charge Q times R. Of course, that's going to be odd under parity transformation because, or at least we think so, because R is odd under parity transformations and Q is just a scalar, it's just charge. So the selection rule for the dipole moment operator determine which atoms or atomic transitions are allowed and which ones are forbidden. I can say that, as we say, it's odd under parity, so this applied, parity operator applied to the dipole operator just gives me minus P sub E. Let's consider a matrix element between the states NLM and N prime, L prime, M prime. So Here we go, n prime, L prime, M prime, parity operator, N, L, M. I can write that as minus N prime, L prime, M prime, pi dagger P sub E, pi N, L, M. Let's play it down. Equals minus N prime, L prime, M prime, minus 1 to the L, P sub L dagger, P sub L operator, minus 1 to the L, N, L, M, which if I can pull this out, it's going to give me minus 1 to the L, plus L prime plus 1 times N prime, L prime, M prime, P sub E, N, L, M. So that's going to give me this as 0 if L plus L prime is even. This is what we call Laporte's rule. It says the matrix elements of the dipole moment operator vanish between states that have the same parity. So that's kind of an interesting consequence of this. So that's all we've got to say for parity. Next time we're going to talk about rotation operators and rotational symmetry.